Okay, thank you very much. It's really nice to be here. As your former postdoc advisor, I was expecting a worse introduction or some other things, so thank you. So I'm very excited to be here today to tell you about direct detection of low mass dark matter, below the proton mass, sub-GeV. And this is really a new frontier which has seen a lot of activity over the past decade. And now there's real experiments coming to the forefront where they have real chance of making progress by a large order of by many orders of magnitude in terms of what kind of dark matter they can probe. And I hope to share some of that with you today. So I want to begin with a big picture introduction. So there's this incredible fact that we don't know the fundamental building blocks of about 85% of the matter in the universe, right? So it's like we just see the top of the iceberg. We don't see what's beneath it. And the matter that we do understand well is described by the standard model of particle physics. And that standard model consists of the quarks and the leptons and the force mediators that mediate the interactions among these quarks and leptons. And those are like the gluon, the W and Z boson that mediate the weak force. Gluon mediates the strong force. There's the photon that mediates the electromagnetic force, and then the Higgs, which is mediates a new force, the Higgs force. And this we understand pretty well. And of course, we're still learning more about it and just trying to understand it better. But the matter we don't understand is this dark matter. And here's a diagram of the energy budget in the universe. So, right, the total energy budget is 100%, and about 5% of what we know is the stuff that's described by the standard model. So the atomic matter, the light, the neutrinos, the things that we can describe with the standard model. About 27% is this dark matter, which we would like to understand, and the rest is dark energy, which I'll completely talk, which we also don't understand yet. Now, there's a lot of evidence for the existence of dark matter. And I assume, so this talk is not going to review that evidence. I assume that most of you are sufficiently sufficiently familiar with the evidence for the dark matter. But it's good to know, what's important to realize that it actually varies by orders and across the scales that cover orders and orders of length scales. So from the smaller scales, from galactic scales, where we've got evidence for dark matter from rotation curves, to galaxy clusters, lensing, gravitational lensing, the bullet cluster, the large-scale structure of the universe, down up to the larger scales of the cosmic microwave background. And to describe these data, the most conservative assumption you can make is that there is some new particle, a dark matter, maybe one or more particles, types of particles, which we call dark matter, that describe these data. And that is a much more conservative assumption to make rather than modified Newtonian dynamics, MOND, or some other thing. Okay. So we're going to go with that, certainly for this talk. So the question that particle theorists like myself and of course others care about is, what is dark matter? So all the evidence we have comes from its gravitational interactions, which creates the picture in the CMB, the power spectrum, the rotation curves, and the large-scale structure and other things. But what we want to know is, what is the density? What type of particle does it consist of? How does it interact with standard model particles? How does it interact? Does it interact with itself through gravity only, or the other forces that it has? What is its mass? What is its spin? Is it connected to the standard model somehow? Is it perhaps part of some larger hidden sectors where there's other particles around as well that it talks to? So this is the kind of questions we want to understand. And the interesting thing is that none of the particles in the standard model can be the dark matter. None of them satisfy the requirements that dark matter needs to satisfy. Now, for many decades, weakly interacting massive particles, or WIMPs, were the favorite candidates. And for many, they still are the favorite candidates. And I'm going to show a mass plot here, a mass axis. So here's the dark matter mass. And the vertical axis is not important for this. WIMPs have a mass between sort of a GeV, few GeV, up to several thousand GeV. And just to orient you a little bit, so I'm going to use natural units. And so that's those. So where I set MC equal to 1, and since E is equal to MC squared, right, the energy that you see here, these MeV, GeV, TeV are energy scales. Those are just measuring the masses. And just to orient you, the electron has half an MeV mass, right, 511 keV. Proton is a little bit less than a GeV. The top quark is the heaviest fermion we've discovered, about 170 GeV. So that's where some of the familiar standard model particles lie. And WIMPs have a mass between about the proton up to well above the top quark. Okay? And outside this region, it turns out that particles that interact, that are WIMPs, that interact with the weak force, so with the WZ bosons or the Higgs, so this weak force often refers to this animal, the weak force, so interacting with the WZ boson or the Higgs, these particles can lie between this mass range. So I'm not really explaining why, but let's just take it let me just assume it for this talk. Now, WIMPs are great. WIMPs are motivated by several theoretical considerations. It turns out that if you take a particle that has a mass in this range and it's acting with WZ or Higgs boson, then you can get the correct relic abundance. So if you calculate how dark matter interacts with standard model particles in the universe, and you just evolve the universe, you see how much is left over from this dark matter particle, you roughly get the correct abundance that we see, which is a fantastic coincidence, sometimes called the WIMP miracle. Okay. It may have nothing to do with nature, but it's an interesting coincidence. Also, we think there should be new particles at the weak scale anyway, because we have other puzzles like the Higgs. Why is the Higgs mass so light? Called the Higgs hierarchy problem, which I'm not explaining in any detail. But there's other puzzles at the weak where we think there should be new physics at the weak scale, and that new physics often has some new stable particle that comes with it, and that could be a nice dark matter candidate. So WIMPs are great, and there's many ways you can search for them, and so experimentally they're very tractable. Okay. So in particular, over the past few decades, there's been many searches devised, and I'll allude to them again a bit later in this talk, but these searches are very mature. They're great, they're important to do, but they don't require theorists like myself or others to think about how to find them. We have good ways of looking for them. Now, over the past decade, the theoretical efforts, and also now starting with experimental efforts, have shifted to other dark matter candidates that really span a very large mass range. Instead of only considering this mass range here, we're pretty sure dark matter has to be somewhere along this mass range. Okay? So there's this huge mass range from down 10 to the minus 21 eV for a fundamental particle up to the Planck scale, essentially. Okay? Now, it actually turns out we know what the lower bound is. We know that a dark matter cannot have a mass less than about 10 to the minus 21 eV. And one simple way of understanding this is that we know dwarf galaxies exist with a size of about 1,000 light years, about 1 kiloparsec, about 1,000 light years. And if you ask, what is the de Broglie wavelength of a boson that has a very light mass? Well, the de Broglie wavelength is given by this lambda here, which is Planck's constant over the momentum. The momentum is just mass of the dark matter particle times its velocity. In a dwarf galaxy of the size, the dark matter has to moves it around 10 kilometers per second, very roughly. And we can just calculate what the de Broglie wavelength is of such a particle, and it's about 1 kiloparsec if its mass is about 10 to the minus 21 eV. And if you make it lighter than this, the de Broglie wavelength is larger than this, and you can't really form structure on the scales where we observe structure to be. So very roughly, a boson that's a dark matter particle has to have a mass larger than 10 to the minus 21 eV. Now, for fermions, they actually have a much stricter bound, and fermions obey the Pauli exclusion principle. So we know that actually sets a much more stringent bound, and by the existence of dwarf galaxies, you can ask how many fermions can you stuff inside a kiloparsec scale dwarf galaxy, 1,000 light year scale dwarf galaxy, and it turns out that if its mass is less than about a keV, then again you run into trouble. So we know that if dark matter is a boson, it has to be above 10 to the minus 21 eV, and if it's a fermion, it has to be bigger than about a keV. Okay. So below a keV, dark matter has to be a boson. Okay. Now, there's many dark matter candidates that people have thought about across this mass range. So one famous one, the QCD axion, which was proposed many decades ago. It's very hard to look for, but that lives in a mass range around here. There's warm dark matter around here. There's something called fuzzy dark matter, where you sit right at this boundary, where you sort of have a de Broglie wavelength of order 1,000 light years. Actually, there's also even more heavier dark matter than what I talked about, where you can think about composite dark matter, or even primordial black holes that people have talked about, where there's many, many orders of magnitude higher in mass, where you can even go. So there's a large mass range that dark matter could have. Now, one generic setup about dark matter beyond weakly interacting massive particles, so you can think of dark matter as being part of a hidden sector, or a dark sector. And the idea, or the way we think about dark matter in this case, is that dark matter is part of some hidden sector, which is a set of particles that has its own forces potentially. It doesn't have any of the standard model forces, so this sector does not directly talk to the photon or the WZ boson or the gluons. And then on the other side is a standard model with all the quarks and the leptons and the WZ boson, the Higgs, etc. And there could be some mediator between them that mediates interactions. And this is a very generic setup for dark matter. And it's also a very natural one in some sense, because we know dark matter does not talk to standard model very much. And thinking that it's in some hidden sector with maybe does its own thing, and being still coupled to the standard model with some new mediator, which allows us to look for it in terrestrial experiments, that's sort of a very generic setup. And it allows dark matter to span a vast mass range. Now, hidden sectors are generic in approaches from like string theory considerations. There are a lot of possibilities, right? You see this huge mass range. But one thing that you actually have to keep in mind is that even though I like showing this mass range, it is actually a little bit misleading. Because once you specify a particular type of dark matter particle with a particular set of interactions, then often there's many constraints on it that you can place. And we know a lot about a particular mass regions, depending on the type of interaction. So this plot is a little bit misleading. It's not like anything goes. Once you specify a particular, once you hypothesize a particular interaction for the dark matter, you can often look for it in various ways, and there's constraints that you have to worry about. But nevertheless, there are a lot of possibilities, and it turns out, this is not a talk about this, but it turns out that there's many well-motivated models and many ways that you can produce the dark matter in the early universe from various production mechanisms, which make actually quite sharp and testable predictions for astrophysical as well as terrestrial observables. And I'll allude in the talk as an example. But clearly, we need a broad search program in order to have a hope of identifying dark matter. Maybe we get lucky in one of the experiments running now, but maybe we don't. So we have to, given the broad range of possibilities, we need to look for dark matter in a wide mass range. Now, there's many ways that you can look for dark matter here. So one thing that this hidden sector can do, the dark matter in this hidden sector, it might have its own forces, which means that dark matter might have self-interactions, and that affects how structure forms. And that can then be looked for with astrophysical probes. Or maybe this hidden sector is like the standard model sector in that it has some light particles like the photon, which it can radiate, and then it can form small structures, compact objects, for example. And then you will look for these interesting exotic compact objects, or dark stars, like David Curtin, for example, and Jack Sedford here have worked on. So there's many different things that you want to look for. Now, what I'm going to be talking about is the possibility that dark matter has some interaction with the standard model. There's some mediator here, and we want to look for it. Okay. Now, for that, it turns out that there's many, many experiments that look for WIMPs. There's many WIMP experiments that cover this mass range here. And yes, there are a few experiments that cover other masses, but they're few and far between. And this has really dominated the experimental landscape for a long time. And a vast mass range remains, very underexplored. And the nice thing is, the cool thing is that there's actually several new ideas and new experiments that allow us to explore for various interactions in the coming decade. Okay. Now, experiments don't happen without money, without funding. And of course, you always try to think about what does an experiment cost. The nice thing is that a lot of these experiments actually are pretty cheap, at least first-generation experiments. If you want to probe new parameter space, you don't have to spend tens and tens of millions of dollars. You can actually do it with relatively little money. And I'll explain why a little bit later for experiments. But in the US, there was recently an effort called a Basic Research Needs Workshop for dark matter, small projects, new initiatives. It's quite a mouthful. But this report I recommend for anyone who is sort of not an expert in this field and I want to learn more about what kind of ideas are out there to look for dark matter across this large, large mass range. And the report suggests different kinds of experiments to cover various different regions. So it argues for looking for coherent field searches, accelerators, and also new direct detection experiments, which allow us to explore 30 orders of magnitude below the proton mass, covering a huge part of this mass range. very briefly about these different things, just to sort of give you an idea where they lie. So if dark matter has a very low mass, remember that I talked about the de Broglie wavelength. So for lighter masses, the de Broglie wavelength is larger. So for light masses, it turns out that you have the number of dark matter particles in any given volume, the de Broglie wavelength in particular, is larger than the distance between the dark matter particles locally. So the dark matter actually behaves like a wave, and you can look for it with cavity experiments and various kinds of resonance experiments. And there's been a lot of work going on this. And remember that in this mass range, it has to be a boson. So the types of particles that can exist are, for example, the QCD axion, other pseudoscalar particles, scalars, or vector particles. And the dark matter here in this range has high phase space density, and you would sort of detect the coherent effect of the entire field. And there's many examples. ADMX, which is one of the flagship experiments in the US, which is funded by the DOE, looking for the QCD axion around the micro-EV. But there's many other ideas recently where people are trying to probe a much wider range of parameter space. Now, for heavier particles, the particle interactions with ordinary matter are not wave-like, but more like particle-like. You look for individual particles that interact with the detector. And here, broadly speaking, there's two types of searches. There's accelerator-based searches, and in particular, people have been thinking about new experiments. So for example, LHC, of course, collider experiments like LHC or BEL2, where you collide electron and positron pairs. They have sensitivity to dark matter. But also, people are talking about new beam dump experiments where you take a beam of electrons or protons, hit a target, produce the dark matter in this target, and then you look for the dark matter interacting in a downstream detector, or you look for missing energy from this dark matter. So there's new experiments that have been proposed to look for dark matter at beam dump facilities. And then the other thing, which is going to be the focus of this talk, are new direct detection experiments where we look for dark matter interacting with our detector. And that's going to be the focus for the remainder of this talk after this sort of bigger picture introduction. So in particular, what I want to do, so going back to this mass range here, what I want to focus on is a big hole which was open, is still open, in the direct detection parameter space, which is between about the electron mass, half an MeV, up to the proton mass, or GeV. And this has seen a lot of recent progress, which I want to tell you about. And you might ask, well, why don't I care about heavier dark matter? Well, I do. Those are often easier to detect because they have more mass, they have more kinetic energy, and traditional WIMP dark matter direct detection experiments are often just suited fantastically well to cover this parameter space here. We don't need to invent new or think about new detection concepts. We want to go lower in mass, where the particles have less energy and are harder to detect. And I'll just mention, and if there's time a little bit at the end of the talk, I'll get back to this. A lot of the detection concepts I'll talk about are actually also relevant to probing dark matter down to milli-eV masses, where the particle is still, where the dark matter is still particle-like in terms of how it interacts with the standard model. So I'll focus on this mass range between the electron and the proton mass, but a lot of the stuff I'll talk about can actually extend to quite a few orders of magnitude lower in mass. Okay. So the outline for the rest of the talk is going to be the following. So first I'm going to talk a little bit about direct detection, give you an introduction to this, okay, tell you about the basics. Then I'll talk about detection concepts for sub-GeV dark matter, after also telling you why sub-GeV dark matter can't be probed easily with the traditional WIMP direct detection program. Okay, so how to search for sub-GeV dark matter. And then I'll tell you one example, which I'm very fond of, which is the SENSEI experiment, which I think is fair to say is the first dedicated experiment to dark matter with masses between 500 keV to GeV, okay, in this mass range that I care about. Okay. So I'll talk about, let's start with the direct detection introduction, the basics, okay. So our solar system, right, where we are, is actually inside a huge dark matter halo. Now, of course, we don't see this dark matter halo, but what we can do is we can simulate it. There's one particular simulation, which was actually done many, many years ago. But here's a dark matter halo that was simulated, and this is roughly how it will look like. So it's clumpy, right, and here's the center, and all the stuff here that you see is not stars or doesn't shine. It's not stuff that you see with your eyes. It's just the dark matter. The bright stuff is the dark matter in this case. Now, our Milky Way, of course, we don't know exactly how it looks either. Here's an artist's rendering of it. That's the 2000. Anyway, here's the spiral arms, and the sun, right, is about 8,000 light years, 8 kiloparsecs, about 30,000 light years from the center, and has some spiral arms. So this is all the gas and the barren stuff that we see. And if we ask how they're related, in terms of how it looks like, this is about the scale. Okay, so the visible Milky Way galaxy is tiny compared to this huge dark matter halo that we're sitting in. Now, we're not sitting at any point in this dark matter halo. We're sitting around here, right, 2/3 away in the spiral arms. And the question is, what is the dark matter like around us? What is its density? How much of dark matter particles are there? And that we can actually measure. And Joe Bovey, for example, is an expert in this in the audience. And we can actually measure how much dark matter is around us, because that's the relevant question in terms of asking what kind of signals might we expect in our detectors on Earth. So it turns out that we can measure the local mass density or energy density. And that is about 0.4 GeV per cubic centimeter. So remember, GeV is the mass of a proton. It's about 0.4 protons per cubic centimeter. The thing we don't know the mass of the dark matter, right? So we don't actually know how many dark matter particles are around us, because it depends on the mass. These dark matter particles, what we do know is they're just moving in the gravitational potential of the galaxy. So we know that they're moving at a speed of roughly 220 kilometers per second. Okay? There's, of course, a range, but roughly it's of that order, which means it's non-relativistic. Okay? So it's moving quite slow compared to the speed of light. Okay? Now, we don't know how many numbers, the number of particles, number of dark matter particles is around us, but we can postulate a particular mass. So, for example, if we take 1 GeV, so the mass of a proton for the dark matter, then we would find that each liter of space, like one of these milk cartons here, would have about 400 particles in it. Okay? Right? So my little bottle here will at any given instant. Now, these are moving at a speed of 220 kilometers per second, so we can calculate what their flux is. And again, for a GeV particle, the flux is about 10 million particles that pass through a centimeter squared, like the size of your thumb, every second for a GeV particle. Okay? So hold up your thumb. So 10 million dark matter particles are passing through your thumb every second, if it's a GeV. If you make it an MEV, right, so almost the mass of an electron, 3 orders of magnitude less, then this would go up by 3 orders of magnitude. This would be 10 billion. All right? And this will go up by 3 orders of magnitude, would be 400,000 particles. And just to compare this, so you might ask the question, well, why don't I see them, right? There's so many of them. Why are they not interacting with me? Why don't I feel down all the time, right? Hit all the time from all sides? And the reason, well, so you can see the solar neutrinos, the number of neutrinos coming from the sun, that flux is about 60 billion per centimeter squared per second. Now, none of us is complaining about them, okay? So we don't feel the neutrinos because, of course, it depends on the interaction strength of how strongly these particles interact with us. The neutrinos interact with the weak force. The weak force is weak, okay? So there's actually very small force, and you need huge detectors to detect these solar neutrinos. The dark matter flux, we don't know what it is. It could be much, 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 much larger than the 60 billion, right? So 100 keV dark matter would have roughly the same number of neutrinos per second per centimeter squared as the neutrinos. But we don't know what the mass is. It could be much lower or much higher. The other disadvantage that dark matter has compared to neutrinos is that these neutrinos are produced at quite high energy, MEV energies, whereas these dark matter particles are non-relativistic. They're moving slowly. They don't have much energy. So the question is, how do we detect them in our detectors? How can we look for them? So the traditional Wimp detection concept, if I can call it that, which is fantastic, right? Don't get me wrong. The idea is that you take a detector, you put it deep underground to shield it from cosmic rays, because cosmic rays can mimic your signal potentially, so you want to go deep underground to shield it. You still have to worry about radioactivity, and a lot of work is spent on worrying about this, but you can at least shield from cosmic rays if you go deep underground. And you sit there, and you wait, and you wait, and you wait, until hopefully a dark matter particle comes by and hits a nucleus inside your detector. And that nucleus gets a big kick, so it recoils. And that recoiling nucleus inside your detector, which consists of xenon or germanium or silicon atoms or other things, that recoiling nucleus will produce some combination of heat, light, or charge. And that's the signal that you want to look for with sensitive detectors. You want to look for some heat, light, or charge signal that come from some recording nucleus, which comes hopefully from a dark matter particle, not from some other cosmic ray or radioactive background event. And the way the kinematics work for dark matter scattering of a nucleus, you can think of the kinematics like billiard ball scattering. Okay, so white ball here is the dark matter and it's hitting some nucleus. Okay. So people have been very good at putting exclusion curves in this program. For many decades of searching, people have not really found a signal. There are actually some signals like gamma, which is being claimed for many years already, but that is not very convincing. But there's many experiments that have looked for dark matter in this way and haven't found anything. And here's the kind of curve that you see. So here's the interaction strength between dark matter and the nuclei. That's called the cross-section. Okay, it's normalized to nucleon, doesn't matter. So some number, some interaction strength between dark matter and nuclei as a function of the dark matter mass, WIMP mass. So I took this part from something else. They helpfully told you that the dark matter is a WIMP, so they put WIMP mass here. Okay, so here's a GeV, here's 100 GeV, here's 10 TeV, 10,000 GeV. And this is the shape. Everything above in this gray region is excluded. There the interaction is too high, and we would have seen the dark matter if it were around. Now, why does it have this shape? The reason it has a shape, well, first of all, this sharp fall-off of the limit, where the limit gets weaker much, much quicker, that just becomes from the fact that a tiny mass dark matter particle is not able to give a lot of recoil energy to the nucleus. So it's like having a little table tennis ball hitting a big billiard ball, a nucleus, and this thing is not going to do much to the nucleus. It's not going to give much energy to this. On this side, this looks linear, and the reason it is linear is because there the problem is not the energy sensitivity. You're able to see these events easily, in quotes, but rather it's the rate dropping. So the rate is proportional to the number density of particles, which, like we said, we don't know. That's rho, the energy density or the mass density over the mass. The mass we don't know, the rho we do know. So the rate just drops as one of the mass. So as you increase the mass, there's just less dark particles around, so the limit will just weaken on how strongly the dark matter can interact with the nuclei. Okay. So there's a lot of work going on over the past few decades, amazing work in terms of making bigger detectors. So there's a lot of constraints. So here's a plot which just shows sort of the best constraints. So everything with a solid line is a constraint from an experiment. Everything with a dashed line are projections for future experiments that are going to happen. So here's, again, the dark matter interaction strength with the nucleon, the cross-section, as a function of the dark matter mass. Here's a GeV, that's the mass of the proton. Here's an MeV, roughly the mass of an electron. And you see this huge bounds down to very low interactions from Lux and xenon 1 ton lately, where the interaction has to be super tiny in order not to have been seen by one of these detectors. So these are big xenon-based detectors. And there's projections from even bigger detectors, LZ, where they're going to use about 10 tons, several tons of xenon, liquid xenon, to look for dark matter at these heavy masses. And these are projections for a 200-ton or 100-ton argon experiment, dark side here, and xenon n-ton is also there. And at low masses, slightly lower masses here, that's with super CDMS, which Miriam, for example, can tell you much more about, where they're going to probe this lower mass region below where the sensitivity of the Lux and xenon detectors and argon detectors peter out. So that's the current landscape. And what you notice, so first of all, what you notice is that I'm seeing a lot of other constraints that were placed inside this bound here. But what you see is that the WIMP program is active, it's important, it's exciting, it's great, okay? And they might find dark matter. But the question that I want to ask is, what about this low mass region here? And the conventional wisdom is that there's no sensitivity to dark matter with mass well below GeV. This is just really, really hard to probe. And the question is, can we find dark matter here in direct detection experiments? The message actually already direct detection constraints down to about 500 keV. And in particular, also, we expect significant improvements from, for example, SENSEI and other similar experiments. Okay. Now, before I tell you how to look for this, let me just ask the question. Why would I think that small experiments, and small also means cheap, inexpensive, why could small experiments in principle probe orders of magnitude of new sub-GeV dark matter parameter space, while I need to spend tens of millions of dollars to probe high mass dark matter here? And there is two answers for them. One answer is that the event rates are actually quite large down here. So remember, as I lower the dark matter mass, there's more of them around. In order to probe the same cross-section, same sensitivity, the same interaction strength, I need a smaller target because there's more of dark matter particles around. And just to show you, for example, I just hypothetically imagine some helium detector, some detector which has helium atoms in it, and I ask for a gram of helium, how many times would a dark matter interact with my helium if it has this interaction strength? And I would see that, and I would ask in an hour, so if I have a gram detector running for an hour, I would see one event if it has this interaction strength. If I have a gram detector running for a day, I would see this interaction strength. And if I have a gram detector running for a year, I would see this interaction strength. And if I go low in mass, a 10 microgram detector could probe this running for a year. So you see that the scales I'm talking about are gram scale running for order days, or years if you go down here, whereas here I need multi-ton years to probe new parameter space down here. And part of the reason, of course, is that not only that I have more dark matter down at these low masses, but the constraints are weak. Okay? So event rates are large. The problem is not the event rates, they're huge, but rather the question is, how do I get sensitivity to these low masses? How can I have detectors that are sensitive enough to these low energies? And then the second question is, can we understand the background events that also happen? Would you believe an experiment that claims the discovery of dark matter? Are you sure that this experiment has really taken care of all the backgrounds? Because at lower energies, you're sort of probing a new region of parameter space where there might be new backgrounds that we haven't thought about before. Okay, so I want to now talk about the detection concept. Okay, how to look for sub-GeV dark matter. So you cannot use elastic nuclear recoils for the detection for light dark matter. And the reason is simple. It's just that there's a very inefficient momentum and energy transfer. So this tiny dark matter particles comes in, hits the nucleus, it's just not going to give much energy. So what you need to do is you need to think about different detection concepts. And one of them, or sort of a class of them, are to look for inelastic processes, where you don't look for elastic scattering of the dark matter of the nucleus, but you look for other inelastic processes, where it turns out that you're able to transfer much more of the dark matter kinetic energy to the nucleus. So one idea is to look for dark matter scattering of electrons. And this is an idea that's several years old, but only now we're sort of getting to experiments that can really look for this with sort of sizable detectors, and where the hope is also that you can control the backgrounds. So the idea is that instead of hitting the nucleus for the dark matter, it comes in and hits the electron and ionizes the atom. This electron recoils. The electron gets ionized, okay? And it produces a signal of at least one electron. And if it has enough recoil energy, this electron might actually ionize other atoms. So you might actually get few electrons, like 1, 2, 3, 4. Might get some range of electrons. Okay. Now the nice thing about dark matter electron scattering is that the kinematics is very different to dark matter nuclear scattering. The kinematics, sort of think about it schematically a little bit, is that here what you have, so let's think about dark matter between the electron mass and the proton mass. So the dark matter is heavier than the electron. Okay, so here's my electron, which I have here now as a tennis ball. Here's my heavy dark matter now. The dark matter, remember, in natural units is moving at about 1/1000th of the speed of light, a few hundred kilometers per second. Okay, in natural units, this is this. The electron velocity, the velocity of a bound electron, what is that? Think about the hydrogen atom. The electron has a velocity in the Bohr model in the hydrogen atom. The typical velocity of the electron in the hydrogen atom is about alpha, the fine structure constant, 1/137. So it's about 10 to the minus 2, okay, 1/100. And you see that the electron actually moves much, much faster than the dark matter. So what you can imagine is that if you have a detector which obviously contains electrons, and the dark matter comes by, and you want to ask how does it interact with the electron? It actually makes more sense to go in the rest frame of the dark matter, with the dark matter sitting there, and the electron spinning really fast, moving around its nucleus, it's around the proton, and the electron will just bounce off this dark matter with a momentum that's essentially just given, where the momentum transfer is essentially just given by the momentum of the electron. So it turns out that you can transfer a lot more momentum by looking for dark matter electron scattering than just the momentum that gets transferred when the dark matter scatters elastically off a big nucleus which you can't move around. So it turns out that you can principally transfer the entire dark matter kinetic energy to the electron rather than just transferring some tiny fraction of it to when you hit the recoiling nucleus. So the kinetics is very different, and in particular that allows you to probe much lower masses. Now, how low in mass can you go, and what kind of targets, materials do you want to look at? So let's do a little calculation. What's the mass threshold? So imagine now that I've got some atom where the electron has some binding energy delta E. And we're going to do a very simple calculation. What is, which is true, so I'm not proving it completely, but I'm claiming that you can transfer the entire dark matter kinetic energy to that electron. And let's ask, how low in mass can I go? So binding energy delta E. At the very minimum, in order to overcome this binding energy, I need to have the dark matter kinetic energy, a half mv squared, to be bigger than this binding energy. So then I can just manipulate this equation using a sophisticated technique called algebra, right? So I solve for MDN, and I've got the dark matter mass needs to be bigger than this delta E over half v squared. And I can ask, for some delta E, for some particular system, what is my dark matter mass? Now, there's an unknown here. It's the velocity of the dark matter. So I mentioned that the typical dark matter velocity is a few hundred kilometers per second. But it actually turns out that there's also a maximum dark matter velocity, which is just this galactic escape velocity. If the dark matter moves too quickly, it's just going to fly out of the gravitational potential. So we know that the dark matter particles around us should have some maximum velocity. And it turns out that that's a few factors of a few larger than typical one. It's about 600 kilometers per second. Okay? So just putting 600 kilometers per second in here, I can solve for the mass. And what I find is that for a binding energy of 1 electron volt, I can get down to 500 keV dark matter. Okay? So I can probe 500 keV dark matter if I've got some system where the binding energy of the electron is 1 eV, and I'm able to detect that. If the binding energy is 10 eV, then I would probe down to 10 times this, 5 MeV. So this now helps me think about what kind of target materials do I want to look at. So one of them are noble liquids, xenon, argon, for example. There, the binding energy of the outermost electron is about 10 electron volts. Okay? So think about the hydrogen atom. There, the binding energy is 13.6 eV. If I've got some big nucleus like xenon, the outermost electron still has a binding energy of about 10 electron volts. And that means that with my formula, for 10 eV, I can probe down to 5 MeV dark matter masses. If I can look for dark matter scattering of electrons, ionizing this atom, and then seeing single electron events. I need to be able to see single electron events. Another very good system, or another very good material to look at, are semiconductors, or even scintillators. So what are semiconductors? So semiconductors, they are things like silicon or germanium, where you've got, if you think back to your basic solid-state physics, there's some filled shells of electrons called the valence band. That's where the electron lies. So this vertical axis here, you can think about energy. So there's some filled shell full of electrons. Then there's a little gap called the band gap. And then there's a conduction band. And if I'm able to get electrons inside this conduction band, then I can manipulate them and potentially see them. And those gaps, those band gaps, are about 1 electron volt. So if I go back to my formula, right, that means that if I can see one single electron inside a silicon atom, inside a silicon crystal, for example, in my semiconductor, I could potentially probe down to 500 keV dark matter. Okay, that's my mass threshold. So there's been a lot of work going on in this, and I'll tell you more about this in a second. But I should just mention that there's a lot of other materials that people have been thinking about, like superconductors, where you've got Cooper pairs, which are very loosely bound pairs of electrons, which are with a binding energy of about a few millieV or millieV, where if you could see the dissociation of a Cooper pair, you would be sensitive to keV dark matter. And there's also Dirac materials. and other materials. And one fun thing about this field is that you get to talk to your condensed matter colleagues and your solid-state physicists and think about what kind of materials are out there and how can you potentially use them for dark matter. So the thing I want to focus on are semiconductors, in particular silicon, where I want to discuss this in a little bit more detail. Okay. So now let me talk about the SENSEI experiment. Okay. Now, SENSEI stands for Sub-Electron Noise Skipper CCD Experimental Instrument. What does this mean? This will become clear in a few minutes. Okay. So we have a collaboration of about 20 people. It's a fully funded experiment, supported mainly by the Heising-Simons Foundation as well as by Fermilab. And 4 institutions, Fermilab, Stony, Brook, Tel Aviv, and Oregon. And it's a nice group, small group, so every person gets to be involved in sort of lots of different parts of an experiment. We have a picture, so you know we're real. It doesn't matter. So what does SENSEI do? So SENSEI's target material, SENSEI's target material is silicon, but in particular, it's special silicon CCDs. So what is a CCD? So a CCD is a charge-coupled device. So here's a picture of some random CCD that I found online. And the idea of CCDs is that light that hits the CCD gets converted to electrons, and then it gets read out, and you can create images. And CCDs are used all over the place. I'm sure there are experts in the audience who know much more about all the uses of CCDs. The astronomy friends make us jealous because they use these to create beautiful pictures. Okay. They get used in astronomy all over the place. But we want to use them as to look for dark matter. So SENSEI's target materials are special silicon CCDs. So here's a picture of a CCD, of a skipper CCD. It's a tiny little device. And this device has about 1 million pixels. Okay. So let me explain this a bit more. So this device is very thin and consists of about 1 million pixels. Here's sort of a zoom in. So here's the CCD. These pixels are about 15 micrometer by 15 micrometer, and the thickness is about 500 micrometer or so. So very sort of thick. It's quite thick compared to an individual pixel, but then there's about 1 million pixels. And the idea is that the dark matter comes in, hits the silicon, one of the electrons inside the silicon, which is inside one of the pixels. This is the energy band. So here's the valence band. The dark matter comes in, hits an electron in the valence band, excites this to the conduction band, and the dark matter goes off and does what it wants to do. And here is, and the idea is that the dark matter would create one or a few electrons in a particular pixel, depending on how high this initial electron gets excited. And this event rate, of course, how many electrons per pixel you get depends on the interaction strength. Okay. So here's the spectrum of electrons that's produced by dark matter for some hypothetical dark matter particle. Okay, so I'm taking a 10 MeV mass for some particular interaction strength. It turns out that this is actually a viable model that's not ruled out by anything else. And here's the number of dark matter events as a function of the number of electrons that are created. So you see that for this particular dark matter candidate, I would create about 1,000 one-electron events, about 100 two-electron events, etc. You see this sharply falling spectrum. Now, calculating these rates is challenging, and that's why you go to your condensed matter friend to ask them to help you, because the electron is part of a many-body interacting system. It's part of a crystal. So it actually is non-trivial to calculate these wave functions of the electron and calculate the rates correctly. Now, before June 2017, the best detectors that existed were sensitive to about 10 electrons or more. So they were sensitive to events that had a signal down here, more than 10 electrons. But for dark matter electron scattering, it doesn't want to produce that many electrons typically. It wants to produce fewer electrons, and you're missing this huge, huge dark matter event. Okay, huge potential dark matter signal. Now, the skipper CCDs are sensitive even to single electron events. And I should say that SENSEI was not the only sort of breakthrough or advance in this field in terms of detecting single electrons, but SuperCDMS and also Danae are 2 separate efforts where they use different technology, and they've demonstrated single electron sensitivity, which I can talk about afterwards in the question and answer session. For now, I'm going to focus on the skipper CCDs. So how do you measure the charge? So here's my schematic of my CCD. Okay, so here's the different pixels. Now the CCD, the way it gets read out, so there's a special row called the serial register down here, and here's where the readout happens. And the idea is that, let's say you create some number of electrons in various pixels, so I've just populated 3 different pixels here. The way you read it out is that you shift all the charges down by 1 to get to this serial register row. And then whenever you do a shift, you shift this to the right, and you keep shifting it and keep measuring the value of each pixel, the charge in each pixel. And then here in this case, all of them are empty except finally this thing gets there. And when you make this measurement, how do you make this measurement? So you can think of this as being a little capacitor, charge to it, which creates a voltage. So we're actually measuring a voltage. And whenever you make a measurement, there's an error. There's an error in this case in the voltage measurement, which translates into an error in the number of electrons you've actually measured. And then you just repeat this and eventually read out the whole CCD. Now ordinary, not skipper, but ordinary scientific CCDs, they have an error, a root mean square readout noise of about 2 electrons, which means that every time you make a measurement, you're uncertain about, you have uncertainty of 2 electrons of what you actually measured. So if you have 1 million pixels and you're reading them out, you can imagine that sometimes you will measure 5 electrons, sometimes you will measure -5 electrons, sometimes 7, sometimes -2, right, for an empty pixel. So there's a huge error, and it's very hard to look for dark matter that just produces 1, 2, or 3 electrons with a device that has such a bad, in quotes, error. Okay. Now the skipper CCD, the way it works is that it's basically the same thing as an ordinary CCD, except the only thing that's changed is this readout. And what you're able to do, in a nutshell, is that you're able to measure the same charge packet multiple times, and then you take an average, and then you reduce your noise. So all you do is you repeatedly measure the charge, and you can do this non-destructively, so as you shift the charge back and forth, you're able to read this charge and measure it multiple times, and you're able to just take, you're able to reduce this noise by taking the average of all the measurements you've done. So you just keep shifting it back and forth and measure it 100 times, 200 times, 1,000 times. And then you take the average of all the measurements. And the average, just from basic statistics, the average of all the measurements is going to have a noise that's reduced by root n, where n is the number of samples that you've taken. Okay, so these were developed by Fermilab in collaboration with Lawrence Berkeley National Lab, the Microsystems Lab there. And they were demonstrated in 2017, and here what they allow you to do is they basically allow you to count the number of electrons precisely in each pixel with essentially no noise. Okay. So here's a picture of a traditional CCD, a measurement, where you're measuring pixels that have no charge in them. Some of them have 1 electron, some of them 2, some of them 3. And you make this measurement, and this is your inferred measurement, just making one single measurement, like an ordinary CCD. And in this particular case, what we had a noisier CCD, so that the error was 3 electrons for one measurement. So you see this big Gaussian. You don't know what you're measuring here, right? If it's 1, 2, 3, 4 electrons or whatever. But if you take a skipper, in this case 4,000 repeated measurements, you see precisely all the pixels that have 0, all the pixels that have 1 electron, all the ones that have 2, 3, 4, etc. Okay, and so this was a project, and now you can do a very sensitive search for dark matter, because now you can look for single electron events, the 2 electron events, 3 electron events, very precisely. And now you also know why it's called SENSEI, sub-electron noise, so below an electron, the noise, skipper CCD, that's what you're using, an experimental instrument, because that's what it is, I guess. Okay. Okay. So what you can do is you can take one of these CCDs and now do a dark matter search, all right? So we had first results for SENSEI using a prototype skipper CCD back in 2017 and also 2008. So we packaged a tiny little CCD, 0.094 grams, was packaged and tested for dark matter search in 2017, and also took data in 2018. And these detectors are tiny, okay? Just to show you, this here is the size of the detector, okay? So this is a cardboard piece. The experimentalists didn't give me a real thing, of course. But this is just a piece of cardboard. But this shows the dimensions. Okay, that's the prototype. Actually, it's misleading a little bit because this cardboard is much thicker than the actual CCD. The actual CCD is 200 micrometer thick, okay, which is much less than this. But the detectors are tiny, but yet you're able to do new science with them. You're able to probe parameter space that hasn't been probed before. Right, that goes back to the idea of having small experiments to do something new. So here's the first results that we were able to get. So here's the dark matter scattering cross-section of electrons now, not nuclei, because we're probing electron interaction in this case, as a function of the dark matter mass. The scale here is not GeV, it's MeV. Here's 1 MeV, here's half an MeV. And you see that with tiny exposure, so we had one run that was on the surface, which we used had an exposure of about 0.02 gram days. Compare this to the multi-ton years that LZ or so will have. And also we took this at the Minos facility near the Minos Hall at Fermilab, that's what we call this Minos here, with a huge exposure of 0.246 gram days, okay, in which we're able to probe this. And as I mentioned, CDMS also had great success with a prototype detector, and they set this limit at the time a little bit before we set this limit here. So they also have sensitivity down to essentially half an MeV dark matter. Okay. So here's a picture of the not the CCD, of the detector. So the CCD is some tiny little device in here. Okay, it doesn't matter. Here's some data that we took. Doesn't matter. Okay. Yeah. So this was prototypes, but we expect better sensitivity from the real experiments and from science-grade CCDs. And the science-grade CCDs are huge. They're this big. Okay. Much bigger than the prototype. And they're also thicker a little bit. And with those, we hope for better performance and better sensitivity. And the goal that we have is to put together 100 grams of these, which is about 50 of these CCDs, okay, of this size, and put those at Snow Lab. And this is a funded experiment, and we hope to do this by the end of this year. And just to show you what the sensitivity is for a particular dark matter model, here it is. So this is a 100-gram year exposure compared to the existing limits from other experiments. Remember I mentioned to you that other experiments can do this. So I mentioned atoms like liquid xenon or so as possible probe. So xenon 10 actually sets the best constraint for some models. They were sensitive to single electrons as well, but with a higher threshold. Okay, but there's other, basically this is the SENSEI limits, the old ones. And we can probe orders of magnitude of new parameter space once we get proper amount of mass together. And the fun thing is that a 100-gram detector will probe new parameter space of taking only 1 hour of data, essentially. Okay. So small, cheap experiments can do a lot. Okay. And here's a picture of the actual CCDs as well. All right. Now, just to give you one example, I alluded to these sharp, testable models that exist. So here's a particular model where you can calculate, you can write down interaction between the dark matter and the standard model through a dark photon in this case, and you can get there's a particular way of producing this dark matter, and that gives you a particular range of parameters that you want to probe in, which is so-called Friesen dark matter. The details are not too important, but there's sort of viable, simple models that exist that you can probe with SENSEI and also other experiments. Now, in terms of, and there's other models that exist as well, go by various names. Okay, I've got some backup slides if anyone's interested. Now, SENSEI is the first step in using skipper CCDs to probe dark matter. There's also another effort called DAMIC-M, which is going on. They're also going to use skipper CCDs, and they're going to have about 1 kilogram of them. They're going to run in Modan. They're funded, fully funded, and the goal is to start taking data with a kilogram detector in about 2023. And they're going to ideally do a factor of 10 better, assuming that backgrounds, etc., are under control. And recently, remember back in the beginning of the talk, I mentioned this basic research needs workshop from the DOE, the Department of Energy in the US, and they actually funded a 10 kilogram, or the R&D, the research and development towards a 10 kilogram detector called Oscura. And running at it for 3 years, you get a 30 kilogram year exposure where potentially you can probe even further down, assuming again that you can control backgrounds, etc. Okay. Now, how much time do I have left? 2? 1, 2? Okay. Okay, good. Let me just mention a couple of things to finish up. So one thing that I mentioned at the beginning is that I said that there's similar detection concepts that you can use, or similar detectors, to probe down much lower in mass. So remember that below a keV, the dark matter has to be a boson. So in that case, there's models like where the dark matter could be a dark photon, or a scalar, or a pseudoscalar like an axion, where the way you can look for that dark matter is that the dark matter comes in and gets absorbed by the electron. Just like an atom can absorb a photon, the electron can absorb a photon and gets excited to some higher state, the dark matter can actually get absorbed by the electron. And in that case, the entire mass energy of the dark matter is gone. And if you have got a silicon detector like, if we have a detector like silicon with a band gap so you can look for bosonic dark matter down to 1 electron volt. So the scale here, this is a particular model, dark photon dark matter, where you can look for bosonic dark matter down to 1 electron volt, well below this MeV scale that I was talking about the whole talk. So there's another way where you can look for other types of dark matter candidates. Okay. So now backgrounds are super, super important, but unfortunately I don't have time to talk about them. Okay. Super CMS has great success, which I'm also not going to talk about. But I'm going to just end up with showing you that what I've showed you here is sort of one concrete idea that is so far is being successful in terms of realizing an experiment where we can go well below the traditional WIMP direct detection bounds and direct detection searches. And there's many ideas that are out in the literature. So I've worked on this topic for several years. There's other groups that have done a lot of work on this topic. There's experimentalists catching up with amazing detector technology that they're developing. And we hope with using different materials, so I'll talk about novel liquids here, scintillators, semiconductors, I mentioned scintillators briefly. There's other materials you can look for, semi-metals, polar materials to probe potentially even lower in mass. I mentioned superconductors briefly. And also ideas not just to look for electron interactions, but also nuclear interactions, where you can use molecules, for example. So there's an idea that collaborators and I had to use molecular gas to look for dark and nuclear interactions. And again, polar materials, superfluid helium, and other ideas. There's a lot of activity in this field where people are thinking about ways to go beyond traditional WIMP detection. And while SENSEI is making great progress, there are other experiments like super CMS in particular, which are strong competition. And there's also a lot of R&D efforts that are progressing very fast, where we hope to probe, orders of magnitude below the traditional WIMP masses. Okay. So to summarize, the goal, right, that we particle physicists have is to uncover the identity of dark matter. And one thing that I want you to take away from this is that compared to, say, 10 years ago, a much wider class of dark matter candidates are now being considered very actively. Okay? People are thinking about a vast mass range with lots of different kinds of interactions to really try to maximize our chances of finding dark matter. I talked about direct detection of low mass dark matter. This is now possible, and there's several ideas, many ideas, several proposals, and now also several concrete experiments which are going forward. And in particular, also talked about SENSEI, which has the first results from prototypes. And the hope is, assuming everything goes well, that we can really probe large new regions of uncharted territory in the next 1 or 2 years. So thanks very much.